All right, so we'll start our today's session related to CUDA memory. Um, yeah, thanks, Ashwin. Right. So we looked at CUDA computation aspects yesterday, and the way this course is structured is that the primary basic computation related aspects which happen more often are taught first, and then whatever is required to deal with optimizations is coming a little later. So we have divided it as computation, memory, synchronization, and then the further topics. One of the other aspects which I thought might be helpful to some of you when you were talking about how to identify issues on the that are happening on the GPU, you might want to refer to these slides, which we are not planning to cover in this course, but might be helpful to some of you. So I have shared the link inside the chat. Um, So let's delve into this. So the CUDA memory part, which turns out to be an important aspect from the perspective of uh, dealing with performance issues. The reason being that accessing various, let's say, computation-related aspects, when it creates a bottleneck, the bottleneck is much smaller. But when it comes to memory, since memory is not on chip, the amount of bottleneck that it can create or the latency it can achieve can affect the performance of the application considerably. For example, we talked about the global memory, right? So we said that this is the CPU. This whole thing is a GPU, slightly expanded version. It has a global memory, which is our usual RAM. Whatever we do with CUDA malloc, that gets allocated from this global memory. And a kernel is usually associated with something called as a grid. So whenever we launch a kernel, it's associated with a nomenclature called grid. And within a grid, there are going to be different thread blocks. Right? So the number of thread blocks is decided by X comma Y in the launch configuration. So that X becomes number of blocks. In each block, there are multiple threads. And a group of 32 threads, we call it as a warp, which is not described or shown in this particular diagram. Each thread is associated with a few registers, right? So that is also what happens on the CPU. So in the case of CPU, we have instructions happening, and then those are being executed on a particular hardware core. That hardware core will have access to certain registers, right, to keep track of, let's say, accumulation of values or what is the stack pointer, instruction pointer, etc. So similar such registers are available for each thread. And then, like on the CPU, we have, after the registers, the memory hierarchy contains L1, L2, L3,
Hi,
and then the main memory.
can you hear me?
Yes, Amir, go ahead.
So this grid, block, and thread, these are particular for any configuration. These number are fixed, correct?
Well,
Total
these are kind of conceptual aspects, in the sense that grid is that way a conceptual aspect. So that term is given because sometimes we want to identify how many thread blocks we have in the system, right? So that is decided by something called as griddim.x or griddim.y, etc. So whenever there is a kernel, the launch configuration of that is called as a grid.
Okay. So M and N that we are passing is basically block and threads.
Blocks and the number of threads within that block. So M becomes the number of thread blocks.
Blocks.
Correct.
Number of blocks. Yeah. Okay. Good. Thanks.
Right. So in case of CPU, we have this hierarchy as registers L1, L2, L3 memory. Right. What that means is that accessing registers is very fast. These are on chip typically. L1 is also most of the times on chip, whereas L2 may not be on chip, depending upon which hardware we are talking about. So as you go from registers to L1 to L2 to L3 to DRAM, the access latency goes on increasing. That is the amount of time we require to access the data into from these types of memories. That goes on increasing, and therefore we want to have as much data closer to the CPU as much as possible. And why do we need that? Because CPU is much faster than the DRAM, right? So the memory access might take large number of cycles. it could take even a few hundreds of cycles, right, to CPU cycles to go to the DRAM, fetch the data, and therefore we bridge that. Whereas the CPU is very fast, right? So we say that 3 gigahertz, 3 into 10 to the power 9 cycles per second, right? So that is a large difference, and we bridge that gap using different levels in the hierarchy L1, L2, L3. So this cache that we talked about in the context of CPU, a similar cache exists for the GPUs also. Just that that cache gets divided into two parts. One part is maintained by the hardware. For example, in case of CPU, when we write a C program and execute it, we don't really worry about which variable goes into a cache, right? That is decided by the hardware at runtime. In a similar manner, on GPU also there is L1 cache, which is L1, L2 caches, which are programmed and managed by the hardware. But there is a small amount of L1 cache, which is also given to the programmer. So you can decide that which variable I want to put into this particular cache memory, right? So that might turn out to be useful when you want to consider the last pieces of performance improvement in our parallel program. So that small part of L1 cache, which is given for the programmer, is called as shared memory, and we are going to study that later in this class. Meetesh has a question: do GPU memory lookups also require VAPA addressing using TLBs, page table walkers, etc.? Yes, all of that happens on the GPU exactly in the same manner as happens on the CPU, right? So there is a notion of virtual memory on the GPU as well. I don't know if they maintain TLBs or not. I have not heard of this, but I would believe that there will be some TLB processing coming into picture. Although I'm not sure to what sophistication that is implemented on the GPU compared to what happens on the CPU. Like in the CPU, we have this complete operating system which is maintaining these page tables, etc. But we don't have full-fledged operating system on the GPU, and therefore we might not require the full gadgetry of the operating system, because the access time is kind of very important. So although there is some virtualization happening, I don't know to what extent it is. That is, whether we have these large page tables, inverted page tables, etc., that is happening in the that happens on the CPU, whether it also happens on the GPU. But that virtualization definitely exists. Okay, so this global memory is the primary one, which is large amount of memory, and therefore almost all our data needs to be stored into this. But it has a large access latency, right? So 400 to 800 cycles as typical values. Then there are texture and constant memories, which I'll for now skip. But those are like constant memories in the sense that these are read-only memories. You cannot change the values in them. You'll have to change the values from the CPU, and then while the kernel is accessing, these are both read-only, and these are very small amounts, 12 KB and 64 KB, and therefore these are primarily used only for maintaining some sort of metadata or parameters that you might require for your training purposes or testing purposes, etc. So there are ways in which specific API we need to use to access the texture and the constant memory. These are not common unless you are using some amount of graphics computation or metadata, but all of this is still possible to be optimized using shared memory. So therefore I'll skip this for now. How much global memory generally have for GPU? Sandeep is asking. So typically the amount of memory that we have on GPUs can span from, let's say, 12 GB memory or 16 GB memory or 32 GB memory. On Volta, we have 16 and 32 GB memory, whereas on A100, we might have around 80 GB of memory, and the recent Grace Hopper architecture might have more than 100 GB memory. Shubham says, which is responsible for translation of address in GPU? The CPU does that for GPU, or GPU has independent page table, or is it handled by software? Yeah, so I don't know how much of that page table handling, etc., happens on the GPU, but CPU is not involved in all this translation. This whole thing is given to the GPU, who is an independent device which takes care of everything. Interestingly, many of these aspects are also undocumented by NVIDIA, right? So whether there is a page table or not, etc. In fact, what is the associativity of the caches, etc. All of this people have tried to reverse engineer by trying a few programs and trying to go back from the access pattern, how the organization will be. So many of these things are not even documented. So I'm not sure if we will find all this information online. But if you find, please let me know as well. Right. So, but CPU is not involved in this translation. It is handled totally by the GPU. Can we harness multiprocessing on GPU? Well, yes, to an extent, in the sense that we can have multiple kernels simultaneously running on the GPU. Shikhar says at max 1024 threads can access per block shared memory. Also, what's the effect of warps in this case? We'll come to shared memory in a while, Shikhar. At that time, we'll take up this question. Okay, so let me move ahead and talk about there are other caches, right? So for example, L1 and L2 caches are present, and I have marked L1 cache as L1/share. So the L2 cache is slightly bigger, close to an MB, but it is shared across all the streaming multiprocessors. So we said that a streaming multiprocessor is a hardware device such that a thread block gets assigned to an SM. Okay, so this streaming multiprocessor uh, uh, has an L1 cache associated with it, right? But the L2 cache is shared across all the SMs. So there is single L2 cache, right? Similar to DRAM. And that can have an advantage because if it is shared, then the communication across SMs, right, needs to go via L2 cache. You don't have to go all the way to DRAM, right? So that will be helpful in the case of some sort of atomic instructions when we deal with synchronization tomorrow's class. L1 cache is closer to the GPU, closer to the core, and it is usually configurable. So it's around 64 KB per shared memory, but it is configurable as, let's say, L1 cache, which is managed by the hardware, and then some scratchpad memory, some shared memory, which is accessible to the programmer. So we'll program that towards the end of this class. And then there are registers. There are large number of registers because there are large number of threads. So each thread should get some chunk of this set of registers, and therefore there is a large register file associated per SM, right? So there are 32,000, right, 2 to the power whatever 15 or 16 number of registers available per SM, right? So that is a very large number because we have a large massive multi-threading happening on the GPU. Sandeep says, does each block has its own separate L1 cache? That is not fully correct. At the hardware level, it is only the SM which has the L1 cache, but that gets context switched and multiplexed across multiple blocks, right, that we assign to each SM. Right? But at the hardware level, it is only at the SM level. If 4 blocks are resident on an SM, does 4 blocks share L1 cache? No, they share it in a time multiplex manner. Right? So that is an SM is going to have one L1 cache, right? And this L1 cache is, if there are 4 thread blocks, then those are going to be using that same L1 cache, right? And therefore, as you can see, if one thread is using a cache and another thread wants to access it, then one thread's data might not be relevant to the other, right? And that's also something that happens for L1 cache as well, that one thread block at the thread block level, one thread block is accessing and that data might not be relevant or even not accessible to the other thread block. Therefore, we might have to even purge the cache, I mean, evacuate the data and load it, except in cases where some context information can be stored. So if your usage of a cache is small enough such that you can store the data into some registers, then that happens. Otherwise, it spills to the main memory. Or, yeah, so let me put it that. All right, so this is just a brief overview. Let's get into the interesting aspects of dealing with memory now. So 2 important aspects that we need to worry about, 2 concepts. One is bandwidth, another is latency. Bandwidth says that how much amount of work I can do per unit time. That is, how many memory access operations I can finish in unit time. That is defined, that decides your throughput or bandwidth. So the GPUs are meant to be bandwidth oriented architectures, which means that instead of a fast bus meaning the connection between CPU and GPU, or the connection from the core to the memory, right? So instead of having a fast data bus, The GPUs are programmed for or devised for a wide data bus. Right? So that is to say that if we are going back to our Mahabalipuram trip, I'm not interested in a fancy bus which goes very fast. I'm interested in large number of buses such that many people can be accommodated together. Right? So that is related to throughput and bandwidth. So because of this, there is a large parallel data transfer that can happen between core and the memory, right? And sometimes between CPU and GPU also. These are two different connections that I'm talking about. But in this context, it is between the core and the memory. The latency says is about the fastness of a single link, right? So how fast I am able to access the memory from the core, right? So that decides the latency, right? So the CPUs are typically latency intensive architectures, which means that we always try to reduce this latency of accessing one element at a time or every element at a time. Whereas the philosophy of GPUs is we want to optimize for the bandwidth. Right? It's okay to have a slow data bus. And there are multiple ways in which the bandwidth can be improved. For example, you can share or reuse the data. Right? So which means that if I have allocated some CUDA malloc memory, I don't want to deallocate it and create another array for the next processing. If this particular data usage is done, maybe I can reuse this because the data is already on the GPU memory. So I might want to make use of it. Maybe it is there in the cache also, in which case I might be able to make use of writing to it and it will get eventually transferred to the main memory. I should also reuse the data as much as possible. To reduce the bandwidth, I can compress the data because then the amount of data that I need to transfer reduces. Right? So that is another optimization that's possible. I might want to recompute the data. Sometimes the data that you require, let's say I want to do something like across multiple threads, I want to compute some average. Right? So n is given and I know the number of threads. Every thread actually knows the number of threads. So what I could do is that one way is that one thread computes it, the average. The problem size n divided by blockdim.x is going to give you the number of threads per thread block, or griddim.x, which gives you the number of thread blocks. So griddim.x multiplied by threaddim.x is going to give you the total number of threads available on the GPU. So that can be done by one thread, and then this computation, whatever is the output of this computation, that can be shared across all the threads. So I write it to a memory location, and then every thread reads from this memory location. That is one way. But this computation is really very small. And the access latency all the way to the main memory, because the one thread is going to write to it and other threads are going to read from it. That is going to probably take several cycles. So instead of that, one of the ways is that you can recompute. Let every thread recompute because the values are constant, right? The problem size is fixed and the griddim.x, blockdim.x are also fixed. So every thread can actually compute. So it's a recomputation happening in every thread, but it might turn out to be still overall faster. The second aspect is latency. We actually want both. The bandwidth should be large and the latency should be small, but that is not always feasible. The priority is given to one of them, on CPU to latency, on GPUs to bandwidth. So the
Sorry to interrupt, sir.
Yeah, sorry, Shane, go ahead.
Yes. So can you once more explain that point? What do you mean by recomputing than doing store and fetch operations in the previous?
Right. So there are multiple ways in which this can be done. One example that I give is that each thread can compute something as a redundant computation. Right. So for example, the example that I was given is that I want to find out the average amount of work done by each thread. Right. So that is problem size divided by number of threads. This division could be done by one thread because this value is going to be fixed. So one thread can do it and then share it with all the other threads, right, via global memory. That is one way. But then every thread might just do a recomputation of this particular computation because accessing global memory might be slower. Other example is that maybe there is some computation I had done and now the data has changed and I want to recompute this. So one way is that I can store this previous computation into memory, right? Some x by y or let's say x to the power y, some computation that I have done. And one way is to store it into a temporary variable. Right? But that temporary variable, if it maps to a global memory, then I'm going to go all the way to memory and get that data when I require it next. Instead, if it is fast enough on the GPU, you might as well want to recompute x to the power y, which might, because it is happening on chip, you don't have to go all the way to global memory, and therefore you might as well want to recompute instead of storing it as a temporary variable and then fetching it later. So there is a store and a load happening, which actually can incur hundreds of cycles, hundreds of CPU cycles, whereas x to the power y might be doable in a few tens of cycles, CPU cycles. So that is where the recompute can turn out to be helpful for small computations.
Understood, sir.
Shubham says, do you also compress the data while caching the data in the GPU? No, no, no. At that time, there is no compression happening by default by the hardware. There is something which one can do as part of the software implementation of improving the bandwidth.
Sir, I'm not clear on how these approaches are helping you improve the bandwidth. I mean, like recompute, then store and fetch or like.
Yeah, so see, finally we are interested in ensuring that when we say bandwidth is the number of operations done per unit time, essentially we want to reduce the total amount of time taken by each thread. Okay, so in one thread, whatever kernel processing we are doing, that is our total computation, which is being repeated across all the threads. If we reduce it for each thread, then the number of operations we finish per second is going to reduce as well. So in this case, individual operations might access memory at different places, right, in our computation steps. Instead of accessing memory, if I can recompute it immediately, instead of a few hundred cycles, I might be able to finish it in a few tens of cycles. And that is going to improve the overall, I mean, of course, the length of one thread's execution is going to reduce, and that is going to help us improve the overall work being done in a lesser amount of time. And that is going to improve the overall bandwidth. Okay, so I'll move ahead. So the latency is the amount of time that we require to fetch the data, right? So ideally it should be 0, but to reduce the latency, essentially we have these different levels, L1, L2, L3, RAM, and in some newer architectures, L4 also. Latency hiding on the GPUs is not done in a traditional way, the way it gets done on the CPU. Right? On the CPU, the way we hide latency is exploiting this L1, L2, L3 RAM hierarchy. Right? GPUs also have that, but that is not the primary way in which it gets done. Okay? The reason being that on the CPUs, we have only a few tens of threads. On CPUs, we have only a few tens of threads. So when we are dealing with L1 cache, only one or two threads will have, or typically one thread will have access to that L1 cache, right, which is running on that core, and therefore its data is available in the L1 cache, that thread's data that is required. Right? Let's say I'm initializing a large array. Okay, it is going to bring the first block of data into the cache line, initialize it, it will bring the next block and so on. Right? And maybe I'm going to make use of it. So that data is probably going to be available to me in the cache itself. So that reduces the latency. I don't have to go all the way to the memory. In case of GPUs, the way it handles is that whenever a particular thread or a warp is trying to access some data, and that data is unavailable, right, in the L1 cache, then you have to go and fetch it from the DRAM, right, from the global memory. During this time, the CPU is sitting idle. I mean, the core is sitting idle. The GPU core is sitting idle. Instead of sitting idle, what we can do is that take another thread or another warp, which is ready for execution. And the chances of finding another warp which is ready is high when you have a large number of threads or large number of warps assigned to execute on the GPU. And therefore, what the GPUs end up exploiting are the massive multi-threading that is available. That is, we have large number of threads, large number of thread blocks assigned to an SM. And therefore, if one block gets blocked, then another block might be taken for execution. Or one warp gets blocked, then another warp can be taken for execution. Right? So that hides the latency, and I'm going to show it pictorially here. So assume that this is the time direction, and there is one thread block which is executing. So at some point, it is going to encounter a stall. Stall meaning it is expecting some data to be available, and that is not available, right? And to retrieve that data, I require some amount of time, which is shown as the brown box here, right? So this is execution, correct execution, and then at some point it gets blocked. So during this time, I might have another thread block available, which I can take up for execution, so that this time is saved. So I use this time, the core was busy. This time also the core was busy. And now the amount of time the core is idle has reduced just by having another thread block in this picture. And I can repeat it. I can have other thread blocks. And whenever they get stalled, I can take up some other thread block for execution. This I can do at the thread level, I can do at the warp level, I can also do at the thread block level, but typically it gets done at the warp level. Okay. At this stage, so the core is busy even during this time, the core is busy even during this time. What happens at this stage? At this stage, maybe I don't have any other thread block, but the first thread block's data is available and I can take that up at this stage. And therefore, I have reduced the amount of idle time of the core, and that has improved the overall execution efficiency. Any questions on this? You can ignore that super linear part, but any questions on this?
So the warp switch is cheap, sir.
Sorry, I didn't hear that. The warp says?
Switch, I mean the warp switch between warping is cheap. That is why it is fine.
Will the switch between yeah, so there is a context switch happening, right? So that, thanks for Abhishek for that question. There is a context switch happening from one warp to another, right? And this requires you to whenever there is a thread switch happening on the CPU, we need to store the context, retrieve the context of the new thread, etc. Exactly in a similar manner, we also need to store the context of the current warp and fetch or retrieve the context of the next warp. This also needs to be done on the GPU. Thankfully, there are large number of registers available such that this context switch becomes very fast, in the sense that you don't really copy back the data. You have the context available for the currently executing warp. You keep it as it is and switch one pointer to start execution of the next context if it is available. If it's a new warp, then you have to create that context anyway. But switching across context is very fast on the GPU, and that gets utilized to improve this latency ID. Good. Any other questions? Okay, so I'm going to move ahead. When we are dealing with memory and caches, the locality is important part, right? So we said that caches have these two kinds of localities. What are those on the CPU?
Spatial and temporal.
Spatial and temporal, right? So those are the two things that we need to worry about. Yeah, so I'll probably skip this. Okay, yeah, so spatial and temporal, right? So when we say spatial, means that in space. So whenever I'm accessing a particular memory location, the nearby locations are also likely to get access, right? So that is called as a spatial locality. Temporal locality says in time, which means that if I'm accessing X now, I'm also likely to access X in near future. So these are two important aspects or principles on which the caches work on the CPU. And it turns out that more often we write programs like this, which automatically have this spatial locality and temporal locality. For example, when we are initializing an array, we access the elements in 0, 1, 2, 3, 4 order. So there is spatial locality. When I'm accessing some important data, right? So I'm computation and doing some computation in a geometry and I use the variable pi, I might use that pi in multiple calculations or some important variables, right? Some parameters. So I might access these again and again. So all of these are examples of spatial and temporal accesses. These, so for example, I'm just mentioning that here as examples. So these happen also on the GPU, right? So the spatial and temporal accesses are also there on the GPU, but these are restricted to typically one thread. Because when I'm trying to access something temporally, yes, then the same variable might get used. When I'm trying to access it spatially, there is a little bit of difference that happens in the context of GPUs that we would like to understand. And that locality is not always, I mean, it's similar, but it's slightly different, which we are going to study in the context of GPUs, right? So so as a takeaway, these localities are applicable to both CPU as well as GPU, but more applicable to the CPU. In the context of GPU, we will have to do something different. Okay, so to understand that, okay, maybe I think we will have to take this up before that, before we get into that locality part on the GPU, which is called as coalescing. So we did matrix squaring yesterday, right? And a general matrix multiplication is essentially done as Cij plus equal to Aik into Bkj, where A and B are input matrices. One of the ways in which I can check if these localities are actually impacting performance is by exchanging these two loops. For example, instead of ijk as the nested loops, as I am mentioning in the first code, I might want to change it to ikj and see if there is a difference. Okay. So when I actually try to do it on my CPU I'm talking about, with some large values of these matrices, then the amount of time that I take almost reduces to half just by exchanging those inner loops. And that is the power that locality can have on the CPU. Okay. And I would leave it to you to figure out why that is happening in the context of GPU, but it has something to do with the access pattern of A, B matrices as well as the C matrix. Okay. So what happens on the GPU, right? So that is our main concern in this class. So on the GPU, what we have to worry about is that how we are doing the initialization of an array, and that is going to give us a hint. So when we say that A of I equal to 0, this is the initialization I want to do, where I is the thread ID. I want to do it in parallel. Then when one thread is accessing A of I, another thread I plus 1 is going to access A of I plus 1. That means that when I am accessing A of I in one thread, I don't have to fetch A of I plus 1 for that thread, which is what happens on the CPU using spatial locality. What I want is when I'm bringing in A of I for a particular thread I should bring I plus 1 for the next consecutive thread. Right? So that is what is essentially going to lead to memory coalescing. So what does the hardware do? It says that the warp threads, which are 32 in number, whenever they access 32 consecutive words, their memory requests are kind of clubbed together into one memory cycle. So in general, on the CPU, when consecutive threads access consecutive memory locations, what's going to happen is those many fetches are required because their L1 caches are different. Right? I understand this properly, right? So when I'm accessing A of 0 to 31 by consecutive threads in parallel, each thread needs to bring A of 0 and nearby data because of spatial locality and A of I into their L1 cache. Right? So these are large number of accesses happening and there is no coordination across threads. So 32 memory accesses might be required if I have 32 CPU threads. On the GPU, when one warp is accessing, the hardware is going to coalesce or club these memory operations together for all the 32 warp threads and fetch all the data in one cycle, one memory cycle. instead of requiring 32 memory cycles. And this we call as a coalesced memory access. This is going to be very important from the perspective of performance, because 32 memory cycles versus 1 memory cycle is a large difference in time. Okay. So, and we'll see how to do that programmatically. So without coalescing, which is what we discussed in the context of CPU, each load store, which means each memory operation, is going to require 1 memory cycle, and therefore the throughput is going to significantly reduce. With memory coalescing, the throughput is going to improve. If that happens, then GPUs are going to be useful only for the compute heavy kernels, and which involve memory, less memory operations, but more number crunching operations, which is usually the case, but that is not always that is not always the case. I mean, there is large amount of data that also is processed on the GPU, and this is a common use case which needs to be supported in the hardware, and therefore the access required to be coalesced. Shubham says, does GPU also do prefetching? I think so. GPUs do prefetching. So many of the architectural aspects on the CPU also translate to GPU, but not fully, in the sense that many of the GPU cores are likely to be in order, for example, right? Whereas we regularly deal with out of our cores when we are dealing with the CPU cores. The prefetching does happen. I don't know how much is the window of prefetching and whether it uses as complicated algorithms as are useful, as utilized on the Intel cores, for example, for prefetching. The buffers that get utilized for prefetching, how much is the history, etc. I'm not sure how much that is documented as well, but definitely to the extent I remember, there is prefetching happening on the GPU also. Shikhar says, in case of non-unit stride, how coalescing will happen? That's a good question. The coalescing will still happen, but in a limited way. For example, if it's a strided access, which means that instead of accessing A of I, each thread accesses A of 2I, then we require 2 memory cycles to get all the 32 words, right, instead of 1 memory cycle. Shubham says, on a warp level or thread level, it usually gets done at the, the prefetching is going to happen. So if I talk in the context, if I divide this in the context of instructions and data, the instruction prefetch can happen at the warp level because the threads are synchronized, whereas the data prefetch might have to be done at the thread level because different threads might operate on different data items. Right? And we'll come to, yeah, sorry, go ahead.
So even here also, each of the threads in the web still have to access all the 32 words from the block, right? So it's still like 32 memory access only. How is it like seen?
So what's is that different threads might still of the warp might still access different words, right? Different, let's say 32-bit elements. So that is okay as long as you are accessing all the 32 threads are accessing consecutive 32 words, right? Aligned also at the 32-word boundary, but anyway, keep that aside. So if they are accessing totally arbitrary words, then one requires 32 memory cycles.
Analyze all these requests and memory requests are collies, we can access in a single memory cycle all of them, sir. So no. So because the memory requests are collies, will we be able to access all the 32, like the 32 words in the block in a single cycle?
That is correct. So in a single memory cycle, all the 32 words, consecutive words, will be brought to, let's say, the processing buffer or processing registers, and then the threads of the warp are going to access these 32 words simultaneously. So because of SIMD execution, if the words are spread across in memory, then until all the words are available for processing, none of the threads of that warp will proceed.
Okay, sir. Thanks.
Yeah, Vipin, thanks for that link. So it says that the memory prefetching is happening on the GPU. Thanks for that. All right, so let's do that for the memory coalescing, right? So when our access patterns are kind of regular, the way we, for example, initialize an array, or the way we access matrices where we are going over the rows, we usually, it leads to memory coalesced access. And pictorially it can be seen like this, where there are different threads, assume these are 32, and they are accessing consecutive words of memory, right? And therefore the access gets coalesced. The uncoalesced access can be represented like this, where arbitrary threads are accessing arbitrary elements in memory, and therefore the number of memory cycles required might turn out to be large. And what do you think about this last access, whether it is coalesced or uncoalesced? Any suggestions? Shubham says coalesced, Chinmay says coalesced. Any other suggestions? Vipin says coalesced. Okay, Shubham Vyas. Oh, there are two Shubhams. Okay, so Shubham Vyas is coalesced. Pirupuraj says coalesced. Harshit says partially coalesced. Sure. So the reason for waiting is I want everybody to think individually what you think about it. And it's okay to think in a wrong way. We are all here to commit mistakes and learn. So it turns out that this happens to be coalesced. So from the hardware perspective, it doesn't matter in which order the warp threads access these memory words. As long as they are accessing in the consecutive words, that is sufficient for the hardware to, because it just fetches all the 32 words, essentially a cache line size into its registers, and it doesn't matter in which order then the threads access. Okay, good. So this turns out to be coalesced. Right. So when you want, whenever your access pattern inside the kernel, right? So this A of ID, where ID is the thread ID, is inside the kernel thread. The access pattern is A of ID, it leads to coalesced access. If your access pattern is slightly different, right? For example, the way it was being, what Shikhar was asking, right? The strided access pattern, what happens? So what is meant by a stride? That instead of accessing consecutive elements, each thread is given a chunk, consecutive chunk, right? So for example, if I have, let's say 1000 problem size, right? And I have 100 threads, then each thread is going to access, let's say 10 elements. It's going to process 10 elements. One way of doing it is that 0 to 9 is being done by thread 0, 10 to 19 is being done by thread 1, and so on. Right? So that is one good way of chunking. That is precisely this threaded access. So how does that look like? When you look at it pictorially, you can see that as soon as the stride length increases, the amount of coalescing is going to reduce, because the words that are being accessed by different threads are going to go away from each other. So as the stride length goes on increasing, you require more and more memory cycles. Okay. The way you will usually do is that there is a chunk size given to you. You can also deduce it based on the problem size and the number of threads available. And the starting that each thread needs to access is thread ID into chunk size. Right? So a thread I is going to access I into 10, for example. And starting address plus the chunk size is going to be the ending address, and I go from start to end and access that A of II. So I'm going to access, as a thread I am going to access these consecutive memory locations. Okay. So this is a very normal way in which we do the chunking, and that turns out to be not amenable towards performance because of this memory uncoalesced access. So what should you do to process this? You have 1000 elements, 100 threads. Each thread needs to access 10 elements, process 10 elements. How should you do the division? I hope this point is coming across, that the strided access can lead to uncoalesced memory access. And therefore, we would like to resolve this such that I still get coalesced access, but still one thread processes multiple elements. Darpan says T1 accesses 1 plus k, 1 plus 2k, whereas T2 accesses 2 plus k, and 2 plus 2k. Okay. Any other suggestions? All right. So we'll take Darpan's suggestion, right? But I would like everybody to think about what is this k. So maybe apart from Darpan, somebody can tell what this k is. Chunk size, okay. Stride length, okay. The Rishikesh says number of threads in war. Okay, so let's understand this, right? So we want that this particular chunk should be processed by consecutive threads, okay, for getting the coalesced access. The number of elements being done by one thread is still going to remain the same, 1000 divided by 10, 1000 divided by 100. But the stride is now going to be decided by the number of threads, right? You can think about that you have 100 threads. So if k is specified as 100, then at one time, T1 is accessing first element, T2 is accessing second element, T3 is accessing third element, and you have fully coalesced access for the first iteration. In the second iteration, T1 accesses 1 plus k or 0 plus k. And that k needs to be the number of items processed in the first iteration. How many items are processed in the first iteration? Equal to the number of threads. So you can take k as stride length or the number of threads, and 1 plus number of threads. So every time you increment your stride by the number of threads, and that is going to lead to fully coalesced access in every iteration. Now, do you need to do it for all the threads? You don't need to. You can do it at the warp level also, as Rishikesh is suggesting, but that is going to really complicate your indexing. Right? But it is sufficient to do it at the warp level, but it is easier to do it for all the threads. Okay, so that is how we will have to worry about. So some things that we are accustomed to on the CPU might have to be done a little differently on the GPU. That is what is the purpose of these. One of the examples of this uncoalesced access happens like this. If you have a random input, then the A of that might turn out to be uncoalesced. Have you seen such a pattern anywhere? A of input of ID, where input is some input array, right? And ID is fixed, right? So that is thread ID. Input is given, but A of input might turn out to be arbitrary. And that is where you might lead to arbitrary memory access. Has somebody encountered this in any of your programs? Histogram, very good. Right, so when you are accessing A of input of ID plus plus, right, that input is arbitrary, right? So it's not sorted, and therefore you might access arbitrary elements and increment them at arbitrary locations in parallel. Ankit says graphs, that's another interesting example, right? Sandeep also says graphs, right? So when you store the graph as adjacency list, not adjacency matrix, then you get into this input of ID. Input of ID is going to be, let's say, it's going to be when I'm trying to access the neighbor of a vertex, right? So I am accessing V, neighbor of a particular element, right? And that element might be stored at arbitrary place, and its connectivity is arbitrary. So vertex 500 might be connected to vertex 0 or vertex 1 million, right? So that connectivity is arbitrary, and therefore sparse representation like adjacency list can get into such uh, uh, non-coalesced memory access pattern, which means that memory processing in graphs and histogram might turn out to be important. So you will probably encounter these terms in the context of memory coalescing, AOS and SOA. Array of structures, which is quite useful on the CPU, and we regularly use, right? We define a structure which contains some elements A, B, C, and then we create an array of those, right? So each thread should access consecutive elements of a chunk or a stride, which means that whenever I access A in a structure, I also typically access B and C in that structure. Shubham says databases. Databases, I'm not sure. Typically, it is column indexed, so if you are accessing different rows, then yes, you are right. So if it is stored as one full row together, then it can lead to a strided access, and therefore that can lead to not really random, but it will be a strided access, because typically the size of each chunk is going to be fixed. But that is one of the reasons on GPUs, when there are in-memory databases stored, those are stored column-wise, right? Because you get coalesced memory access. So that's an important point. Binong says in hash map you have an irregular memory access. That is correct. When different threads are hashing it to arbitrary buckets, and that is probably going to lead to an invalid access. That is correct. So on the CPU, we have these arrays of structures, and if a structure contains ABC elements, fields, then the expectation is that whenever you access some field, you also access other fields, and therefore putting this together improves locality on the CPU. In the context of GPUs, right, we would like to store these in coalesced manner. So if you put the structure together, ABC fields together, that is going to actually lead to strided access. Because when one thread is accessing field A of one structure, at the same time, the next thread is accessing field A of the next structure. And these two accesses are spread out in memory because B and C are occurring in between. So this is similar to our chunked processing, which is shown as the second diagram here. So we would like to avoid that. And therefore, like we were discussing in the context of databases, that you store the columns together. In this case, we'll store all A's together, all B's together, and all C's together. So that leads to 3 different arrays, and we create a structure out of them. And therefore, this is called as a structure of arrays. Right? So I'll show you pictorially and programmatically. So AOS is, I have an array of structures. So I have structure and then an array of all of that, which is common in the CPU. So the expectation is that when a thread accesses an attribute of a node, like A, the same thread, right, accesses other attributes of the same node. This is locality. This is spatial locality. Okay. In contrast, the SOA says I am going to keep all A, all B, all C together, and I'm going to put that into a structure. So this becomes a structure of arrays, and the expectation is that when a thread accesses an attribute like A of a node, its neighboring thread in the same warp accesses the same attribute A of the next node. So whenever thread I accesses all A of I, thread I plus 1 accesses all A of I plus 1. And therefore, for coalesced accesses, these two should be consecutive. I hope this is coming along pictorially. I mean, you are able to visualize this clearly. If there is any question, please ask.
So can you explain why this accessing the same attribute of the neighboring node is also helping in coalescing? This part I am not very
Okay,
confident.
so when I am storing, so whenever, so how the code is going to look like, right, inside the GPU, inside the kernel, you will say some attribute dot a, right, of some entity, right? So let's say we are dealing with a graph, or maybe graph is probably a wrong example, but maybe there is a XY coordinates being stored of different points in a 2D plane. Now, whenever a thread is accessing .x, that is an instruction. I want to access .x value. What is the other thread of the warp doing? That is also accessing .x because it's the same instruction. So when I'm accessing geometry of thread ID .x, the next thread is accessing geometry of thread ID +1 .x, right? And if I want, and the 2th thread is accessing geometry of thread ID +2 .x, right? Because it's the same SIMD instruction, but they are operating on different data items. Now for coalesced access, all these .x, TID, TID +1, TID +2 .x, all of these should be consecutive. If that is the case, the only way I'm going to get it is all .x should be stored together. If not, let's say I'm storing this x here and y here, and then I have a structure of these xy, which is common the way we store it on the CPU, then .x by different threads are going to be spread across. And I'll be able to get only 16 threads able to get their .x in one memory cycle. And I'll have to do another memory cycle to get threads 16 to 31 will have to fetch the remaining .x in the next memory cycle. If I have x, y, z, then that is going to reduce the coalescing further because the stride is increasing. In contrast, if all x are stored together, all y are stored together, then the instruction is going to access all .x, then the next instruction is going to access all .y, and the accesses will be fully coalesced for the 32 warp threads. Does that seem reasonable, Sayan?
Yes, understood.
Okay. Anybody else has any confusion on this? Feel free to ask. It's a very important point from performance perspective when you parallelize your codes. So yeah, so we would like to do CUDA mem copy of this. So how do the codes look like? Now it will become pointers, right? So we'll have to do a CUDA malloc on these. So on the CPU, I'll have a structure. On the GPU, I'll have arrays, which are essentially going to be CUDA malloc using pointers. So on the, if I have to do, I mean, it's not that you cannot do AOS on the GPU, right? So I'm just showing that here. So if I access .a, .b, .c like this with ID, then the next thread ID +1 is going to be spread across, right? So spread across by B and C, and therefore this is going to lead to a strided access, whereas it's going to be A of ID equal to ID, and that is going to lead to a fully coalesced access because ID +1 is going to be just consecutive. Okay, so these need to be, so there will be CUDA malloc for each of these separately, whereas here it is going to be a single CUDA malloc of the structure. Okay, Abhishek says, will non-coalesced accesses contribute to warp divergence? You tell me where is warp divergence in this particular code.
I mean, if you move from AOS to structure SOA, you are that is fine. I mean, but if it is just AOS, then my point was like if different threads in a warp are accessing non-strided or non-coalesced accesses, so if some thread what is the order in which the threads fetch their memory? If there is some ordering, will that order affect the whole warp? Was the intuition from the question.
Right. So the ordering in which the threads access these memory locations will not create a problem with respect to thread divergence. It can create a problem with respect to coalescing But we said that if they are accessing 32 consecutive words, then it doesn't matter in which order they access, right? So only memory access will not lead to thread divergence. Thread divergence will happen only when you have if-else conditions in the code, right? And so these two are kind of independent of each other, the coalescing and thread divergence. You can have coalesced access and no thread divergence. You can have coalesced access, no thread divergence. You can have uncoalesced access with and without thread divergence also, right? So all of these programs can be constructed. So these two are independent entities.
Okay.
Okay, so just as a quick check that whether really AOS versus SOA gives any benefit, when I ran it on my GPU with these two accesses, keeping rest of the code same, it turns out that there is substantial benefit that you get by converting it into SOA, right? So you have to remember to convert it into coalesced accesses on the GPU. Okay, so you might want to copy a linked list from CPU to GPU that you can try offline. I'll skip this. Okay, so we are coming to shared memory. At this stage, we'll take a break and we'll meet at 10:43 or so, 10:43, 44 around that time. So we still have 6 or 7 minutes of break. All right, so I'll stop the recording here so that it becomes manageable.